There is a plastic being manufactured in Tengzhou, Shandong right now that contains no crude oil. Not less crude oil, no crude oil at all. Its primary raw material is carbon dioxide, the same gas that every climate agreement on Earth is trying to eliminate. On the 29th of May 2026, Lavema completed the world's first startup, a 50,000-ton per year polypropylene carbonate unit. First attempt. Qualified products. First attempt. Qualified products on the first run. 4 years of development from laboratory to 50,000 tons. Polypropylene carbonate is a polymer made by combining carbon dioxide with propylene oxide. 40 to 50% of its weight is carbon dioxide. Every ton produced captures and locks approximately 420 to 480 kilograms of carbon dioxide. The material biodegrades in industrial composting conditions. It leaves no microplastic residue. Those two facts together are what makes this different from every previous attempt at biodegradable plastic. Conventional bioplastics like polylactic acid also biodegrade. But polylactic acid requires industrial composting temperatures above 60 degrees Celsius to degrade at the rate its marketing claims. And polylactic acid, when it fragments in ambient conditions before full degradation, produces fragments that behave similarly to microplastics. Polypropylene carbonate degrades through a different mechanism. The carbonate ester linkages in its backbone are hydrolytically cleavable. Microorganisms produce esterase enzymes that cleave these linkages. The cleavage products are small molecules that microorganisms consume as carbon sources. No fragment accumulation, no microplastic formation. And the Lavema plant in Tengzhou is vertically integrated. The carbon dioxide comes from the plant's own industrial processes. The propylene oxide comes from its own 300,000 ton per year propylene oxide unit. Both core raw materials produced internally. No external procurement required. This is not a laboratory demonstration. It is not a pilot project. It is the world's first industrial-scale carbon dioxide-based biodegradable plastic operating in full production. And it is in China. By the end of this video, you will understand one thing clearly: how China solved the thermodynamic problem that kept this material in laboratories for decades, and why the plastic industry is about to face the same disruption that steel, batteries, and solar have already experienced. Here is the part nobody explains clearly. The chemistry of using carbon dioxide as a raw material for plastics has been known since the 1960s. The thermodynamic barrier that prevented it from becoming practical has been understood just as long. Carbon dioxide is one of the most chemically stable molecules in existence. The double bonds between carbon and its two oxygen atoms require enormous energy to break. 799 kilojoules per mole for the carbon-oxygen double bond. For comparison, breaking the carbon-carbon bond in a hydrocarbon chain requires much less energy. Roughly 347 kilojoules per mole. Carbon dioxide is more than twice as resistant to chemical reaction as the bonds in conventional plastic feedstocks. This is why carbon dioxide is the end product of combustion. It is what you get when you have burned everything that can be burned. It has no energy left to give. Forcing it to react requires either enormous amounts of energy, a very clever catalyst, or both. For decades, both approaches failed commercially. First-generation zinc butyrate catalysts required pressures above 50 atmospheres. Temperatures pushed the reaction toward unwanted cyclic carbonate byproducts, not the linear polymer chains needed for packaging film. Porphyrin catalyst systems developed in the 1990s achieved better selectivity, but cost more to produce than the value of the plastic they enabled. The economics never worked. Conventional polyethylene costs under $1 per kilogram to produce at scale. Every generation of carbon dioxide-based plastic catalyst produced material that cost 3 to 4 times more. No packaging manufacturer would pay 3 times the price for a material with inferior thermal stability. The Western chemical industry concluded that carbon dioxide-based plastics were theoretically interesting and commercially irrelevant. China disagreed. Here is the detail that changes the entire chemical picture. The breakthrough that made commercial production possible is the double metal cyanide catalyst system, specifically the zinc-cobalt double metal cyanide formulation, developed at the Chinese Academy of Sciences, commercialized through multiple Chinese chemical companies. The double metal cyanide structure creates active zinc sites at the atomic level, sites that interact with carbon dioxide molecules in a specific way. When carbon dioxide approaches an active zinc site, the zinc draws electron density from the oxygen atoms. That distorts the normally linear carbon dioxide molecule. The bond angle bends from 180 degrees toward approximately 130 degrees. That distortion dramatically reduces the energy required for propylene oxide to attack the activated carbon atom. The polymerization reaction proceeds at 10 to 15 atmospheres of pressure, at temperatures between 50 and 60 degrees Celsius, without producing significant cyclic carbonate byproducts. The carbonate linkage selectivity in modern double metal cyanide systems exceeds 99%. More than 99% of the carbon dioxide entering the reactor ends up in the polymer chain, not wasted, not converted to the wrong product, locked into the plastic. This catalyst performance at low temperature and low pressure is what makes the Livaima plant's economics work. Lower pressure means smaller, cheaper reactor vessels. Lower temperature means less energy consumption per ton of product. Higher selectivity means less waste and simpler downstream separation. The catalyst that took decades to develop is why the Tengzhou facility produced qualified product on its first run. Now here is where this gets genuinely alarming for the conventional plastics industry. The Livaima facility in Tengzhou is not a standalone chemical plant. It is the downstream end of a vertically integrated industrial chain. The upstream starting point is a methanol to olefins unit. Its capacity is 1.3 million tons per year. A 300,000 ton per year propylene oxide unit feeds directly into the polypropylene carbonate reactor. The carbon dioxide feedstock comes from the industrial processes within the same integrated complex. No external procurement, no supply chain risk, no price exposure to carbon dioxide markets. The raw material cost for carbon dioxide at Livaima is effectively zero. This is the industrial symbiosis model that most industry analysis correctly identifies as China's cost advantage. But the Livaima project goes further than the description suggests. It is not simply a plastic factory built next to a power plant to capture cheap exhaust. The same industrial complex produces the propylene oxide and generates the carbon dioxide. Both combine to make plastic, all internal, all on the same site. The internal supply of both primary raw materials removes the two largest cost variables from the production equation. The 50,000-ton scale puts it in a different category from anything previously attempted in this material. China's planned total capacity, 753,000 tons per year, as of 2022 planning documents. The Livaima startup in May 2026 represents the beginning of that capacity coming online, not the end. Here is the Western comparison that explains the strategic gap. The primary biodegradable plastic produced at commercial scale outside China is polylactic acid. Polylactic acid is made from fermented plant sugars, cornstarch in the United States, sugarcane in Brazil. The fermentation converts plant carbohydrates into lactic acid monomers, which are then polymerized into the plastic. The process works. Polylactic acid is genuinely biodegradable. It has real commercial markets in packaging and food service. But the raw material is food. Every ton of polylactic acid produced requires agricultural land, irrigation water, fertilizer, and harvest energy. In the United States, approximately 3 kilograms of corn are needed to produce 1 kilogram of polylactic acid. 3 kilograms of food to make 1 kilogram of plastic. At a time when global food security is a serious policy concern, the land use competition is structural. The United States committed billions in subsidy to polylactic acid production through agricultural policy programs benefiting corn farmers. The agricultural lobby that supports corn ethanol supports corn-based polylactic acid. The political economy of the bioplastics market in the United States is shaped by who benefits from the feedstock, not by which feedstock is most efficient. China does not have a corn lobby. It has an industrial carbon dioxide disposal problem, and it chose to turn that problem into a production input. And the production cost of polylactic acid remains stubbornly above conventional petroleum plastics at commercial scale. NatureWorks, the dominant American polylactic acid producer, has operated for over 2 decades. It has not achieved cost parity with polyethylene. The polypropylene carbonate approach does not use food. It does not use agricultural land. It does not use irrigation water. Its primary input is an industrial waste gas that its producers are currently required to reduce. The carbon dioxide lavema feeds into its reactor would otherwise require carbon capture and storage infrastructure to handle. The plastic production is the carbon capture. Here is the honest part of this story that the technology enthusiasm is not telling you. Polypropylene carbonate has real limitations that explain why it is not already replacing polyethylene everywhere. The glass transition temperature of polypropylene carbonate is between 25 and 45 degrees Celsius. Glass transition temperature is the temperature at which a polymer changes from rigid to rubbery. For polypropylene carbonate, that transition happens at temperatures that occur in a car parked in summer sunlight. A packaging film softening at 40 degrees Celsius cannot be used for products in hot storage environments. Conventional polyethylene remains stable to temperatures well above 100 degrees Celsius. So if this material softens in a hot car, why is China building such a massive supply chain for it? The answer lies in a single, massive agricultural problem. Polypropylene carbonate's thermal stability ceiling is a fundamental property of its chemical structure. It is not solved by better catalysts. It requires blending with other polymers, adding stabilizing additives, or accepting specific application limits. Agricultural mulch films, flexible food packaging in temperature-controlled environments, foam applications and coating materials are the current sweet spots. Hot-fill beverage containers and automotive interior components are not. The biodegradation claim also requires careful framing. Polypropylene carbonate biodegrades effectively in industrial composting facilities at controlled temperature and humidity. In ambient soil conditions, degradation is much slower. In landfill conditions with limited oxygen and moisture, it degrades more slowly still. The zero microplastic claim is accurate, but it depends on the end-of-life pathway being industrial composting, which requires infrastructure that does not exist universally. Here is the application story that shows where polypropylene carbonate is already winning. Agricultural mulch film is the largest current market for polypropylene carbonate in China. Conventional polyethylene mulch film covers hundreds of millions of hectares of agricultural land globally. China alone uses over 1 million tons of agricultural mulch film per year. The plastic residue that accumulates in Chinese farmland is a documented problem affecting crop yields and soil quality. Studies found polyethylene fragments at 30-centimeter depth in fields using mulch film for a decade. A film that biodegrades completely eliminates this problem without requiring farmers to collect and dispose at harvest. The farmer plants through the film. The film biodegrades during and after the growing season. No collection required, no landfill required, no contamination remaining. It suppresses weeds, retains soil moisture, and increases crop yields. Microplastic contamination from agricultural film is a documented problem across Chinese and European farmland. A mulch film that biodegrades completely in soil within one growing season eliminates this contamination pathway. Tianguan signed a multi-year supply agreement with a major Chinese logistics provider. The deal covers compostable packaging films starting in 2026. Inner Mongolia, Mengxi High-Tech developed polypropylene carbonate resin with improved thermal properties for construction and ceramics applications. Zhejiang Hisun Biomaterials listed new polypropylene carbonate and polylactic acid blend grades for thin film applications in 2026. The blending approach addresses the thermal stability limitation directly. Blending polypropylene carbonate with polylactic acid improves barrier properties and adjusts the thermal performance profile. Blending with other biodegradable polymers allows producers to tune the balance of stiffness, flexibility, and degradation rate for specific applications. None of these blending approaches eliminate the fundamental glass transition temperature constraint, but they manage it for the applications where polypropylene carbonate's other properties are competitive. By combining polypropylene carbonate with polylactic acid or other polymers, producers can adjust the balance of properties towards specific applications. A blend of polypropylene carbonate with polylactic acid produces a film with better barrier properties than either material alone, and a lower carbon footprint than conventional packaging materials. The application development across multiple Chinese producers is not running parallel to the Levima capacity scale-up, it is running ahead of it. The market for the material is developing before the full capacity arrives. Here is the geopolitical dimension that the materials science coverage misses entirely. China produces and consumes approximately 40% of all plastics manufactured globally. Its national interest in plastic raw material cost and supply security is proportionally larger than any other economies. Polyethylene and polypropylene are made from ethylene and propylene, which are made from petroleum or natural gas. China imports over 70% of its crude oil. Every ton of conventional plastic in China represents a dependency on imported fossil fuel at internationally set prices. A ton of polypropylene carbonate from domestic industrial carbon dioxide breaks that dependency for specific applications. This is the same logic that drove China's investment in solar panels, lithium batteries, and silicon carbide. In each case, the technology substituted a dependency on imported commodities with a dependency on Chinese manufacturing capability. Solar panels substituted coal imports with domestic photovoltaic production. Batteries substituted petroleum with domestically processed lithium chemistry. Polypropylene carbonate substitutes petroleum feedstock with industrial carbon dioxide. The pattern is not accidental, it is not coincidence. This country produces most of the world's solar panels, most lithium batteries, and most electric vehicles. The pattern is deliberate. In each case, the strategic logic is identical. Identify the commodity dependency. Fund the research to eliminate it. Build the manufacturing infrastructure to deploy the solution. Export the technology to countries that cannot eliminate their own dependency. Create a new form of leverage that replaces the old commodity dependency with a technology dependency. China is not breaking out of the global economic system. It is rewriting the terms on which it participates. It is national industrial policy identifying commodity dependencies and funding research to eliminate them. The 753,000-ton planned capacity figure is not a market forecast. It is a policy target. When China sets a policy target for a material technology, the manufacturing infrastructure appears on the schedule the target implies. As demonstrated on the 29th of May 2026 in Tengzhou. Here is what the Western chemical industry has gotten wrong. BASF unveiled a pilot line for polypropylene carbonate-based polyurethane foams in Europe as part of its carbon circularity program. SK Geocentric in South Korea announced capacity expansion for polypropylene carbonate polyols targeting automotive and construction foam markets. Novema in the United States has been developing carbon dioxide-based polymers since the early 2000s. The Western industry is aware of the technology. It is not uninterested. It is slower. The same pattern as every previous materials transition where China led. Western chemical companies evaluate new technologies through standard capital allocation processes. New plant, new feedstock, new catalyst system, unproven at scale. The risk-adjusted return does not compete with expanding existing production of established materials. The decision is rational from the perspective of a single company's capital committee. It is strategically wrong from the perspective of an industry facing a supply chain restructuring. By the time Western produces complete capital approval and permits, Levima will have been operating for 5 years. 5 years of process optimization, 5 years of yield improvement, 5 years of product development with customers, 5 years of cost reduction through operational learning. In specialty chemicals, 5 years of commercial scale experience is the moat, preventing new entrants from competing on cost. Competitors are not just behind on capacity. They are behind on everything capacity teaches you. China's Tianguang Group has been operating commercial polypropylene carbonate production since 2006. 2 decades of experience before Levima opened its 50,000-ton plant. 2 decades of process optimization. 2 decades of quality control refinement. 2 decades of customer development. 2 decades of understanding what the material can and cannot do in real production environments. That accumulated knowledge does not appear in a patent. It appears in yield rates, defect rates, and customer scores of a company producing since before competitors finished laboratory demonstrations. Here is the full picture. 380 million tons of plastic are produced globally every year. The overwhelming majority from petroleum feedstock. Every ton of conventional plastic produced contributes to 2 outcomes: carbon dioxide emissions from the production process and persistent plastic waste that accumulates for centuries without biodegrading. Polypropylene carbonate inverts both outcomes. Its production consumes carbon dioxide rather than emitting it. Its disposal generates no microplastic residue when properly composted. 40 to 50% carbon dioxide content. Every ton produced captures 400 to 480 kilograms of carbon dioxide. The Levima plant captures up to 24,000 tons of carbon dioxide per year in its products. That is carbon dioxide that never becomes plastic waste in the first place. This adoption pattern keeps repeating across the industry. The market is growing at 6 to 7% per year globally. The technology that was commercially irrelevant 10 years ago is commercially operational at 50,000 tons per year today. That gap between irrelevant and operational is where fortunes get made. The glass transition temperature limitation is real. The composting infrastructure requirement is real. So is the 20-year head start. And the production cost premium over conventional petroleum plastics remains real at 20 to 40%. But cost premiums close as scale grows, and the scale just changed. Subscribe if you want to follow where this leads, and leave your answer in the comments. The world produces 380 million tons of plastic per year from crude oil. Industrial carbon dioxide costs zero. China controls the catalyst and the scale. What does the plastic industry look like in 2035? Tengzhou is answering that question. China solved it first. China built the catalyst. China built the integrated supply chain. China built the 50,000-ton plant. And now China is building the experience base that will determine who produces the next generation of plastics. Patents can be licensed. Experience cannot. The same question applies to every previous materials competition. Who will control the manufacturing infrastructure when the market is ready? In solar panels, batteries, and electric vehicles, the answer was China. In polypropylene carbonate, the answer is already being written. It is being written in a chemical plant, not a press release. In Tengzhou, Shandong. As of the 29th of May 2026, the first industrial-scale evidence that carbon dioxide can become the raw material of civilization, not its waste product. And the answer will determine who the petrochemical industry of the 22nd century works for.